Everyone, what's up? Welcome back to my tutorial channel. Daniel's here, and today I'm back to give you a tutorial in probability and SMP preparation. In today's lesson, I'll be talking about frequently used continuous distribution. So in continuous distribution, there are totally 9 basic distribution: uniform distribution on interval AB, normal distribution, exponential distribution, gamma distribution, Pareto distribution, beta distribution, log normal distribution, chi-square distribution, and Weibull distribution. However, today I would like to focus on the first 4 distribution. Then next video, I'm going to talk about the last 5 distribution. And one thing I want you to notice here, on the exam, usually the question will fall into the first 4 distribution. So make sure you go over these 4 distribution. The last 5, sometimes we did have question about these 5 distribution. However, those questions are quite rare. So I suggest you to practice harder on the first 4 distribution. So now let's start off with the first distribution, uniform distribution on an interval AB. So similar to discrete distribution, whenever you start working on a distribution, you have to ask yourself certain question. The first question is, what is the density function? The second question for a continuous case is, what is the distribution function? Then what is the mean, what is the variance, what is the moment generating function? So first, the density function PDF of uniform distribution on interval AB is 1 over b minus a if a less than b less than a less than x less than b, and the density function is 0 if otherwise. The distribution function is capital F of x. So the density function is f of x, and the distribution function, this is the CDF, is capital F of x. And capital F of x is defined by 3 cases. If x is less than or equal to a, then the distribution function, the CDF, is 0. If x falls between a and b, then f of x is x minus a over b minus a. And the last case, if x is at least b, then f of x is 1. Capital F of x is 1. This is how the PDF and the CDF of uniform distribution look like. So here, suppose you look at the first picture. The PDF of x is 1 over b minus a if x between a and b. Outside the ranks a and b, f of x is 0. And the mean of this distribution is basically the midpoint between a and b. So e of x is a plus b over 2. For the distribution function, the CDF, basically the CDF is the ratio between the shaded area and the whole area. So here the shaded area is the dark area right here, and the whole area is this rectangle. So f of x is the ratio of the shaded area over the whole area. So it's basically to x minus a over b minus a. So f of x here means probability that x less than or equal to x. So if the question asks for the probability that x is at least x, then we look for the y rectangle. So it becomes b minus x over b minus a. The probability that x falls between C and D is the ratio between this shaded area and the whole area. So it's basically just d minus c over b minus a, because these two rectangles have the same height. The bottom of the shaded area is d minus c, and the bottom of the whole area is b minus a. So the ratio between these two rectangles is just d minus c over b minus a. So that's how you compute probability in uniform distribution. And honestly, in continuous distribution, uniform is the easiest one because the probability is distributed evenly. In uniform distribution, the mean is the midpoint, which is a plus b over 2. By looking at the picture on the previous slide, you can see the mean is basically just the midpoint on the picture. Or you can use integration to prove this expected value. So to find expected value of x, the expectation, we integrate from a to b x times f of x dx. So this is integrate from a to b x over b minus a dx, and this is a plus b over 2. To find variance, remember variance is basically ex squared minus ex whole square. So to find variance, first of all you have to find ex squared. So ex squared is integral from a to b. We integrate from a to b x squared f of x dx. And we got this is b squared plus ab plus a squared over 3. So variance of x is basically ex squared minus ex whole square. So we have b squared plus ab plus a squared over 3 minus a plus b whole square over 4. So to derive these formulas, we have the final answer for variance is b minus a whole square over 12. And the last important thing to learn in uniform distribution is the moment generating function. So remember, the moment generating function is just expected value of e to the tx. So we basically take integral from a to b e to the tx over b minus a, because 1 over b minus a is the f of x. And this becomes e to the tb minus e to the ta over t times b minus a. So that was about uniform distribution on an interval a to b. Now we look at the second distribution, normal distribution. So before I start working on normal distribution, I want to stress that normal distribution is extremely important in SMP. Not only in chapter 7, but also in chapter 11 when you work with risk management. Risk management is basically work on normal distribution. So pay attention to normal distribution. This is the most important distribution in SMP. So for normal distribution, we start with the standard normal distribution. That means this normal distribution has a mean of 0 and a standard deviation of 1. The density function of standard normal distribution is phi of x. This is phi of x. It's basically just notation. We usually use f of x for continuous distribution, but for normal we can use phi of x. So this phi of x means the density function, the PDF. And this is equal to 1/2 e to the negative z squared over 2. And the domain of z is negative infinity to infinity. In normal distribution, the mean and the variance of standard normal distribution, mean is 0 and standard deviation is 1. Just right here at the introduction. Z follow normal 0, 1 has a mean of 0 and a standard deviation of 1. So remember, variance is just like standard deviation square. So in this case, for standard normal distribution, the variance is also the standard deviation, which is 1, because 1 square is just 1. The moment generating function, mz of t, is e t squared over 2. This one can be proved by using integrating from negative infinity to infinity of e to the tx f of x dx. Here we use z. And by the way, for standard normal distribution, we usually use z. as a notation for the variance. And for the general normal distribution, we can use any capital letter, but for standard normal distribution, usually we use Z. Now we learn how to compute probability in normal distribution. So the density function of the standard normal distribution has a bell-shaped graph. So you can look at this. This is a bell shape. It's symmetric, center at 0, and unit model. That means we have a unique mode. The shaded area is represented for probability that Z less than or equal to Z. For normal distribution, basically we assume that the area under the bell shape, the density curve. This is called the density curve. So in normal distribution, we assume that the area under the density curve is 1. So the whole area here is 1. So the probability that Z less than little z is the shaded area. So to find this probability, we basically calculate the ratio between the area of the shaded area and the area of the whole area under the density curve. And for normal distribution, the standard normal distribution, on the exam, you are given a Z table. This is the Z table, but this is not the full version. On the exam, you will be given the full version of the Z table. This is just for illustration, so I took a picture of a small corner of the Z table. So how do you read the Z table? Here we have the vertical index and the horizontal index. So Z, D2, the first line and the vertical line give you the value of Z, and the numbers with 4 digits behind decimal point is the probability or the area. So basically, for example, if you want to find the area to the left of Z, you're going to use this table. For example, if I use Z as 0.71, the way you read the table is basically you look for 0.7 at the vertical line and you look for 0.01 at the horizontal line right here, because 0.7 plus 0.01 is 0.71. So basically we look at the intersection between this column, the column of 0.01 and the row of 0.7. So you got 0.7611. So this number 0.7611 represents the area to the left of the z-score 0.71. So if you want to find the area to the right of this z, remember the complement rule. We take the whole area, which is 1, subtract the area of the shaded area. So that's become 1 minus 0.7611. And what if, remember for normal distribution, you have, for standard normal distribution, you also have negative value of z. So what if on the exam, you are given only the positive table, but the question gives you negative value of z? How do you find the probability? So by symmetry, phi of nib z is 1 minus phi of z. So imagine you have another line here that is just minor of this line. So you see this is the area to the left of this imaginary line is the probability that z less than nib z. And by symmetry, this area is exactly the y areas right here. And the y area is 1 subtract the shaded area. So basically, the rule is phi of nib z is 1 minus phi of z. By the way, I want you to pay attention to one more notation. This phi is called a capital Phi and represent for the CDF. You also have the phi, the regular phi, that's represent for the PDF. So pay attention to the notation to make sure you're not gonna get confused. So suppose the question asks you to find capital Phi of nib 0.71. You basically follow the rule. So 1 subtract 5z, that means 1 subtract 0.7611, and you got 0.2389. So that's how you find probability corresponding to negative z value. So that's how you compute it. That's how you compute the probability of standard normal distribution. Now we go to the general normal distribution. So the general form of the normal distribution has mean mu and standard deviation sigma. The PDF of general normal distribution is f of x given mu and sigma square is 1 over square root of 2 pi sigma square exponential of nib x minus mu whole square over sigma square. For x here, the domain is the whole real life. So the mean and the variance of this one, the mean is mu and the standard deviation is sigma. So if you have learned transformation in college algebra, you would be able to understand this transformation. So the normal distribution is basically shift the standard normal distribution to mu and scale by a scale parameter sigma. In normal distribution, we also learn about the moment generating function. So moment generating function for the general normal distribution is exponential of mu t plus 1/2 sigma square t. This formula is extremely important, so make sure you don't skip any detail in normal distribution. Anything in normal distribution is important, so do not skip any. So that's about normal distribution. So we have learned how to compute the probability for standard normal distribution. Now what if you have questions relating to the general normal distribution? So here is the shape of the general normal distribution. Remember, for the standard distribution is center at 0 and the standard deviation is 1. Here for the general normal distribution, the bell shape, the bell is shifted to either the left or the right to center at mu, and the scale represent for the height of the bell. So for normal distribution, because this is symmetric, the distribution is symmetric, so the mean is also the median and also the mode. Remember, this is a unit mode. We have only one mode. So the mean, the median, and the mode are the same, which is mu. Mu is the center of distribution. And sigma square is the measure of how widely dispersed the distribution is. So how do we find the probability that A less than X less than B? So for regular normal distribution, we have to standardize the general normal distribution to the standard normal distribution and then make use of the z-score table. So this is how we standardize the general normal distribution. Let's say X follow normal distribution with mean mu and standard deviation sigma. So we have a transformation here. Let's say z is x minus mu over sigma. Then z will follow normal 0, 1. So basically, remember in college algebra, if you subtract mu, suppose mu is positive, then x minus mu is shift the graph to the right mu unit. So basically, from x, we shift the graph to the left mu unit to center at 0, and then we scale by parameter sigma to have standard deviation 1. So that's how you transform a general normal distribution to a standard normal distribution. So z here is called the z-score of x. So z is x minus mu over sigma, and this z follows the standard normal distribution. And to find probability of a less than x less than b, how we standardize is basically we subtract 3 sides of this inequality by mu, and then divide 3 sides of this inequality by sigma. So we have a minus mu over sigma less than x minus mu over sigma less than b minus mu over sigma. And don't forget, x minus mu over sigma here is z. So we renotate it as z. So here the problem becomes the standard normal distribution problem. We find probability that z is between 2 points. So we use the phi function, capital Phi function. So that becomes capital Phi of b minus mu over sigma minus capital Phi of a minus mu over sigma. So that's how you standardize the problem. So again, if you are given the general normal distribution and you want to compute the probability, don't forget to standardize the problems, because on the exam you are given a very simple calculator that is TI-30XS multi-view. So the TI-30XS multi-view calculator is not a scientific calculator. So you cannot find probability of general normal distribution without standardizing the problem. So again, for general normal distribution, standardize first and then make use of the z-score table. Next, approximating discrete distribution by normal distribution. So sometimes in the discrete distribution, if you are given the numbers sufficiently large, sometimes you can approximate the probability using normal distribution. So in approximating discrete distribution by normal distribution, there are 2 steps. The first step is continuity correction, and the second step is standardization. So to understand the continuity correction, basically discrete distribution, you can work with, you are able to work with single point. But for normal distribution is a continuous distribution, so you cannot work with single value. So to get rid of that miscalculating, we need to manipulate the problem using continuity correction. So if x is the discrete and integer value, then a continuity correction will be applied in the following way. Suppose you are asked to calculate probability n less than or equal to x less than or equal to m. So we can approximate this probability by a new continuous variable y that has the same mean mu and varying sigma square. And y here is normal distributed. So however, it's reasonable to extend the interval nm to n minus 0.5, m plus 0.5. I'm going to explain you more about why we extend this one in a couple more examples. Because like from discrete to continuous, we have to correct the continuity. That's why we have to extend this interval to a little bit bigger interval that cover the old interval. So probability n less than or equal to x less than or equal to m is probability that n minus 0.5 less than z less than m plus 0.5. For example, let's say x follow binomial 6.4. So n is 6 and p is 0.4. So for this distribution, if the question asks you to find probability that x equals 3, you can use the old method, which is using the binomial mass function formula. So that's the first method. The second method is using normal as the approximation. So first we calculate the mean and the variance. So the mean of binomial distribution is n times p, which is 6 times 0.4, that is 2.4. And variance of x is np 1 minus p, so it's 1.44. So we need to approximate this distribution using a continuous distribution follow normal. So let's y follow normal 2.4, 1.44. Remember, the continuous variable that we created should have the same mean and the same variance with the discrete distribution given. So the first step is called continuity. Here, if you want to find probability that x equals 3, suppose you don't use continuity correction. So you use y to approximate x. So this becomes probability that y equal to 3. However, y is a continuous distribution. So if you calculate probability that y equals 3, the answer is 0. But by normal distribution, probability x equals 3 is not 0. You see that? So that's why we need continuity correction. And to use continuity correction, basically we extend 3 to the left and to the right to create a rectangle. Because for continuous, basically we use rectangle. So here we subtract 0.5 to find the low point and add 0.5 to have the upper point. The reason why we use 0.5 here is like we cannot use 1, because if you subtract 1, you are going to calculate the probability of 2 as well and the probability of 4 as well. So we can find any value but not 1, less than 1. It should be less than 1. And usually to make it beautiful, we use 0.5. So that's why we use 0.5 for this one, and because 0.5 is the midpoint, so the midpoint between these two values, so that's why we use 0.5. So after you finish the continuity correction, you are going to use standardization, because Z here follow normal, but the general normal distribution is not standard normal distribution. So we need to use standardization. So this basically phi of the upper bound subtract mu over sigma minus phi of the lower bound subtract mu over sigma, and then you can use the z-score table to find the answer. So that's how you approximate discrete distribution by using normal distribution. Next distribution is exponential distribution with mean 1 over lambda. So the first question, what is the density function? The density function is f of x given lambda is lambda e to the negative lambda x, for x positive and lambda is positive. The distribution function, the CDF, is to basically integrate from 0 to x, and don't forget to change variable. So integrate from 0 to x of f of t lambda dt. You have 1 minus e to the negative lambda x, for x is non-negative and lambda is positive. Survival function is 1 minus the CDF function. So you have e to the negative lambda x. So in exponential function, not only density and distribution function, you also have to remember the survival function, but actually this is very easy to remember. It's just 1 subtract the distribution function, the CDF. The mean and variance. So in this case, expected value of x is 1 over lambda, and variance of x is 1 over lambda squared. These two can be proved using integrate from 0 to infinity of x times f of x, and variance of x is ex squared minus ex whole square. So just use the old method to prove these two. The moment generating function is lambda over lambda minus t, for t less than lambda. So the moment generating function should define when t less than lambda. And by the way, sometimes in some textbook you will see an alternate version of exponential distribution. That is, they use theta as 1 over lambda. So f of x given theta is 1 over theta exponential of naive x over theta. So the expected value is theta, the variance is theta squared. So just make sure that you're not gonna confuse when they give you when the question gives you the alternate version of the density function. And here's how the PDF and the CDF of exponential function look like. Here we consider the case when lambda is 1. When lambda is 1. So the function exponential function just e to the naive x, and capital F of x, the CDF is 1 minus e to the naive x. So this is how the PDF and the CDF look like. And the k moment of this distribution is expected value of x to the k, and this is k factorial over lambda to the k. This formulas can be proved using integration as well. Next, exponential distribution would mean 1 over lambda. So in exponential function, there are two things that you need to pay attention. The first property is called lack of memory property. So if you are given probability x greater than little x plus y, given that x greater than x, this is conditional probability. So we are going to use conditional formula, conditional probability formula. So that's the probability that x greater than x plus y and x is greater than x over probability that x greater than x. And the numerator is just simplified as probability x greater than x plus y. And using the CDF function, this is basically 1 minus f of x plus y over 1 minus f of x. And this is the survival function, right? Survival function is 1 minus the CDF. So we have survival function at the point x plus y over survival function at the point x. The top is exponential of naive lambda times x plus y. The numerator, the denominator is exponential of naive lambda times x. And we cancel out e to the naive lambda x at the numerator and denominator. We have the answer is simplified as e to the naive lambda y. So probability x greater than x plus y given x greater than x is probability x greater than y. So this is called the lack of memory property. So that's how we prove it. But how do you understand this property? The interpretation is, suppose x measure the time from now until the next insurance claim filed by the company, and suppose x has exponential distribution with mean 1 over lambda. So suppose we use x here is 5. So suppose 5 weeks has passed. By lack of memory property, the time measured from now until the next claim is also exponentially distributed with a mean 1 over lambda. So that means like we don't care how many claims has occurred in the last 5 weeks, but the distribution of the time from now until the next claim is also exponential distribution with mean 1 over lambda. That means we forgot what is real to now. So no matter how many claims has occurred in the past 5 weeks, the distribution has forgotten what is real to now. So the probability that x greater than 4 plus 5 given x greater than 5 is basically the probability x greater than 4. This is called lack of memory property. And in exponential distribution, we have the link between Boyson and exponential distribution. So suppose x is exponentially distributed with mean 1 over lambda positive, and we regard x as the time between successive occurrences of some types of events, and n represents the number of events in one time unit. Then n is Poisson distributed with mean lambda. One more, the minimum of collection of independent exponential random variables. Let's say y1, y2 to yn are independent variables following exponential distribution with means 1 over lambda 1, 1 over lambda 2, 1 over lambda n respectively, then let's say z is the minimum value of these n variables. So z is also exponentially distributed, but with a mean 1 over lambda 1 plus lambda 2 plus delta 2 lambda n. So here I want you to know that the minimum of collection of independent is one more important thing in exponential distribution. So for exponential distribution, you have survival function, you have the lack of memory properties, the link between Poisson and exponential distribution, and this property. So we have 4 things that you have to learn in addition. And exponential distribution is commonly seen in the exam. Next, distribution a gamma distribution with parameters alpha and beta, both are positive. The density function, the PDF, is f of x given alpha and beta is 1 over gamma of alpha, beta to the negative alpha, times x to the alpha minus 1 e to the negative beta x for x positive. The gamma function here is defined as integral from 0 to infinity of y to alpha minus 1 e to the negative y dy. If n is a positive integer, then gamma of n is n minus 1 factorial, and this is n minus 1 gamma of n minus 1. This property is very important. The gamma of n is n minus 1 factorial and is equal to n minus 1 gamma of n minus 1. The mean and variance e of x is alpha over beta and variance of x is alpha over beta square. However, we also have an alternative way to express gamma distribution. So let's say theta is 1 over beta, just like exponential. So we set a new parameter. Theta is 1 over lambda over beta. So the function becomes 1 over gamma of alpha, theta to the alpha, x to the alpha minus 1, e to the negative x over theta. So the mean and the variance here, e of x is alpha theta, and variance of x is alpha theta square. So that's how you, so make sure you are used to both ways of expression gamma distribution. Sometimes on the exam, they give you the first version, sometimes they give you the second version, so you have to be mindful when you see a question relating to gamma distribution. And here's how the PDF and CDF of the function look like. So let's look at the first 2 pictures when beta is keep fixed as 1. So here both picture beta is 1, and the first picture alpha is 1, and the second picture alpha is 2. So when alpha get larger, you see that we have more weight to the right. That means the PDF become more weighted to the right and is more spread out. It's more spread out. You see the tail getting bigger and bigger, so it's spread out, and the high getting shorter. You see the high getting shorter. Now we compare the second picture and the third picture. So as beta get larger, you see here alpha is fixed at 2, and beta, when beta get larger, the PDF becomes more weighted to the left and is more peaked, because you see on the second picture the height of the PDF is 0.4, but for the third picture the height goes up to 0.70 something. So when beta get larger, the PDF become more weighted to the left and is more peaked. So we have finished the first 4 distribution in continuous cases. Next video, I'm gonna continue working on the last 5 distribution. Now we are going to work on some practice. Let x be a random variable with a continuous uniform distribution on the interval 1a, where a is more than 1. If e of x is 6 times variance of x, then what's the A? This is a very simple question. I can say uniform distribution is the easiest distribution in continuous distributions. So just write out the formula for E of x and var of x. Here we have 1 is the lower bound and A is the upper bound. The mean is the midpoint, so we have 1 plus A over 2, and the var of x is A minus 1 whole square over 12. And follow this property, E of x is 6 times var of x. We have a new equation. 1 plus A over 2 is 6 times A minus 1 whole square over 12. So that's become A squared minus 2A plus 1 over 2. So we cancel out 2 with 2. We have 1 plus A equal to A squared minus 2A plus 1, and simplify. Bring everything to the left. We have A squared. Bring everything to the right. We have A squared minus 3A is 0. And from here we have A is equal to 3 or 0, but 0 cannot be the value because we expect A to be more than 1. So that was about problem number 1. Now we work on problem number 2. If x has a continuous uniform distribution on the interval from 0 to 10, then what is the probability that x plus 10 over x is greater than 7? So here you see this probability, the left-hand side is not in terms of a variable, but it's a function of variables. So we are going to derive this formulas first. So we have probability that x, and here one thing you notice that x here is positive, right? So probability x plus 10 over x greater than 7 is probability x squared plus 10 over x greater than 7. And because x is positive, because x distributed from 0 to 10, so x is positive. So when you multiply both sides by x, the inequality remain the same. So this becomes probability x squared plus 10 greater than 7x. And this is basically just quadratics. So we factor the left-hand side. We have x minus 2 times x minus 5 is positive, which means either x less than 2 or x is greater than 5. But the minimum value here is 0 and the maximum is 10. Don't forget detail. So basically we have two rectangles, one from 0 to 2 and one from 5 to 10. So the probability of x less than 2 and greater than 0 is 2 minus 0 over 10 minus 0. And the probability that 5 less than x less than 10 is 10 minus 5 over 10 minus 0. The answer is 710. So which is E. E is the answer. So that is the second problem. Now question number 3. A student received a grade of 80 in a math final when the mean grade was 72 and his standard deviation was S. In the statistics final, he received a 90 where the mean grade was 80 and the standard deviation was 15. If the standardized scores, the score adjusts to the mean of 0 and the standard deviation of 1 were the same in each case, then what is S? So basically we have to find a z-score for both distribution and then we set them equal and solve for S. So the z-score of 80 is 80 minus 72 over S, and the z-score of 90 here is 90 minus 80 over 15. This is a very, very basic equation. So we derive it into linear equation, and we have S is 15 times 80 minus 72 over 90 minus 80. So the answer is 12. So B is the answer. That's how you solve this problem. Next problem. Problem number 4 and 5 relate to the following information. 3 individuals are running a 1 kilometer race. The completion time for its individual is a random variable. Xi is the completion time in minutes for person I. So x1 follow uniform distribution on interval from 2.9 to 3.1. x2 follow uniform distribution from 2.7 to 3.1. And x3 follow uniform distribution on interval 2.9 to 3.30. The 3 completion times are independent of one another. Question number 4, find the probability that the earliest completion time is less than 3 minutes. So here we have the minimum of x1, x2, x3 is less than 3. Whenever you work with minimum, before you find the probability, I suggest you to use complement rules. So probability that the mean less than 3 is basically 1 minus probability that the mean is greater than 3. And here you can apply independent properties because the mean of x1, x2, x3 greater or equals 3. That means all of these three should be greater than 3. So we have 1 minus probability that x1 is greater than 3, probability x2 is greater than 3, and probability x3 is greater than 3. And then you can find the probability. One common mistake here, some people use additional rule here, like they think mean of x1, x2, x3 less than 3, so they use either x1 less than 3 or x2 less than 3 or x3 less than 3, but then the problem become more complicated because you have to work with additional rules. So here I use complement rule first, so the problem become much more easier, much more simpler. So now for each of the term, probability that x1 is greater than 3 using the first uniform distribution is basically just 3 minus 2.9 over 3.1 minus 2.9. For the second one, we have 3 minus 2.7 over 3.1 minus 2.7. And the last one is 3.2.9 over 3.3 minus 2.9. And the answer is 0.9625. So rounded to two decimal places, we have B is the answer. Question number 5. Find the probability that the latest completion time is less than 3 minutes nearest point of 1. That means round to 2 decimal places. So here the latest completion time, that means the maximum of these three. So probability that max of x1, x2, x3 less than 3, that's easy. It's just the max less than 3, so all of them should be less than 3, right? So probably x1 less than 3 times probably x2 less than 3 times probably x3 less than 3, and use the uniform distribution. So the answer is 0.09375, and we round to 2 decimal places, so the answer is 0.09. So that is the last problem today. So today we have finished 4 distribution out of 9 distribution, and I repeat, the 4 distribution we learned today are the most important on the exam. The last 5 we should learn, and like don't skip, but I believe we don't have many questions related to the last 5 distribution. It's quite rare. It's not usual that we see questions related to the last 5 distribution on the exam. So thank you so much for watching, and I hope you guys enjoyed my video. I hope my video is useful for you, especially if you are seriously taking SMP. If you like my video, please give me a thumb up, and thank you so much. See you guys next time.